Today we are gonna cover 4.3 working backward with the normal curve table. The lecture notes which is used in this PowerPoint slides are from the elementary statistics, Gibson and Dillard. So let's look at our first example from our book. Suppose a researcher concerned with measuring forms of intelligence in newborn infants sets up an experiment to electronically monitor the neurological reaction time when a tiny light is flashed into a baby's eye. After testing thousands and thousands of newborn infants, it was found that the average reaction time was mu equal to 50 milliseconds with standard deviation sigma equal to 10 milliseconds. Assuming the reaction times are normally distributed, below what value would you expect to find the fastest 10% of the reaction times? When you read the question over here, you will have a bunch of information. And it might be hard to understand the question just reading it. So I'm recommending you to first draw the normal curve by listing real data value and the z-scores. Here you can see the normal curve which we draw, putting our real data values, our mean 50, and when we go to the right side, we are increasing by 10. 10 is our standard deviation. When we go to the left side, we are decreasing by 10. And you can see over here also our z-score values corresponding to these real data values. Next thing we need to do is to shade the area in the question. Our question is asking the value which is below the 10%. So in order to find the value below the 10%, we need to find the z-score at this value. And in order to find the z-score at this point, which I am pointing, we need the area information. And our z-score table is giving the area between 0 up to z-score. When you look at it over here, as you remember, the area information for each z-scores is between 0 up to z value. Let's go back to our question. And we are looking for the 10% below the value. 10% below the value. As we know that normal curve is symmetric, left side of the area is 50% and right side of the area of the mean after the mean is 50% of the data values. So if we are looking for 10%, what is left between 0 up till z-score? What is the percentage of the area? Which is, as you can see over here, which I listed already, 40%. So on our z-score table, we need to look at in the body of the table over here, in the body of the table, we are gonna search what value is close to 40%, which means 0.4. When you look at it, it is somewhere around here, which is corresponding to 1.2 intersection of 1.2 and 0.08. In the table, closest value to 40% is 0.3997. This is giving us the z-score 1.28. Another thing you have to be careful is what side you are looking for. If we are looking for on the right side, the z-score values, if the z-score value is on the right side, it's a positive value. If the z-score, what you are looking is on the left side, it's a negative value. So you need to be careful about this one. So the z-score, what we are looking for is negative 1.28. After finding the corresponding z-score, which is negative 1.28, we need our formula again. Z is equal to data value minus the mean divided by the standard deviation. We know that our mean is 50, standard deviation is 10, and we already found our z-score, which is negative 1.28. We are looking for the data value corresponding to negative 1.28. So using the algebra, when we just substitute z value, mu, and standard deviation, we can solve this equation for x. When you do the cross multiplication, you get negative 12.8 equal to x minus 50. And when you solve this one for x, you get 37.2 or 37.2 milliseconds, which is the value which we are looking for. Next section is 4.4, binomial distribution, an introduction to sampling. I want to look at a two-category population. A two-category population is a population where every member is classified into exactly one of two categories. Here are some examples for two-category population. First example is a medical population example, which is about an experimental drug, and our categories are the users who were cured and users who are not cured. Next example is an educational population example, and it's about the SAT verbal score. The categories are the scores 330 or less and scores above 330. And the last example you see is about the manufacturing population, and it's about the assembly line batteries, and it's classified into batteries defective and batteries not defective. So in these examples, you may notice the p-values. These are the percentages. If you know one of the p-value for an example in the medical population, p is equal to 60%, which is for the percentage of users who were cured. You can easily be able to find the percentage users not cured. If we have 60% is cured, we are left with 40% who are not cured. After we know that we have a two-category population, we may wish to know what we can expect when we sample from such a population. In this example, our population is billions of coin tosses classified into those resulting in heads and those resulting in tails. We may expect that half the time we will have heads and half the time we will have tails. And now, if we were to randomly sample from this population, for example, we sample 12 coin flips, what may we expect to happen? Remember, the sample proportion will be approximately equal to the population proportion. Let's say we dropped 12 coins to the table thousands and thousands of times. Then you would get something like this histogram. This is called a sampling distribution. A sampling distribution shows us what we can expect when we randomly select n values repeatedly from a particular population. In the case of dropping 12 coins, we would most likely expect 50% heads or 6 heads. And indeed, we do most often get 6 heads. This is called the expected value. The expected value can be calculated with the formula n times p. N is the sample size, p is the population proportion. In our experiment, we get most often 50% heads, or if we have 12 coins, which means we have 6 heads, and this is called expected value. Let's look at it with the formula. Our experiment has sample size n is equal to 12 and population proportion is equal to 1 over 2. If we put n and p in our formula, we get expected value 12 times 1 over 2, which is 6 heads. Even though we most often get 6 heads, on a great many occasions, we can get more than 6 heads and less than 6 heads. Now, you may think that, okay, this happens with the coin tosses, but what if we sample a different population? Say we have 60 dice and we want to paint one face on each to red, and we would like to look at the expected value. What's gonna happen? Now you might think that, okay, this happens with the coin tosses, where you are getting the probability of a head for a coin toss is 50%. And what if you sample a different population? Say we have 60 dice and we want to paint one face on each to red. What's gonna happen? What our expected value will be? So we have 60 dices. This is our sample size, and 1 over 6 is the proportion of having painted face. When we calculate our expected value, we will get 10 painted face frequently. However, as we said before, on many occasions, we get somewhat more than 10 painted face, and on many occasions, somewhat less. Again, with the heights of the histogram bars falling off in a shape approximating that of a normal distribution.